Okay, we are going to get started. Hi, everybody. Thank you for joining us for today's webinar. It's another great one. I'm Lauren Armstrong, Marketing Director for Quantum Analytics, and I will be your moderator for today's event. Today, we're going to be exploring how to identify and quantify regulated phthalates in complex matrices using the microfurnace thermal desorption gas chromatography mass spectrometry technique based on the ASTM method D7823. But before diving into this topic, I wanted to give a brief intro to my company, Quantum Analytics. We are a value added distributor of multi vendor instrumentation. We're an authorized distributor for frontier products in the US and Canada, and we specialize in integrating the frontier pyrolysis solution with Agilent platforms. Our menu of technical services includes financing, installation, cross platform integration, training, product support, and entire new lab startup programs. Now, on to today's topic. This topic is going to be super focused on the ASTM method for phthalates analysis. But if you want to dive further into the pyrolysis technique, learn more about the products or accessories mentioned, or get additional background on material characterization, we have a ton of great resources on our website for you to explore. Many of these are actually presented by our today's presenter as well. Um, a few of these resources that I recommend are on your screen right now, but the list is way too long to show here. So please visit our resources library on lqa.com and start browsing those articles, on demand webinars, videos, and application booklets. Today's webinar is the basis of the existing ASTM method D7823 for regulating phthalates using the microfurnace TD-GCMS technique. And to address this topic, I am super excited to welcome my colleague and friend, Rogine Belganet. Rogine is the technical director at Frontier Lab Americas. She's super passionate about creating awareness around the frontier technology and provides technical support to all types of users. Rogine graduated from the University of Houston with a Bachelor of Science in Chemistry, and she started her profession as an analytical chemist, just like many of you, at at Nalco Champion, an Ecolab company, in 2012 as an analytical chemist. She worked with various analytical instruments such as pyrolysis GCMS, TGA, FTIR, and X ray for material characterization, polymer identification, and contamination analysis. Before I turn it over to Rogine, I wanted to give a few housekeeping items. As a registered guest, you're going to receive a link to this recorded webinar in your email when it becomes available, which is very shortly after the webinar typically. This webinar we think will last just under 30 minutes. We're going to open it up to the questions after Rogine's presentation is complete. Type your questions at any time into the question module in the webinar control panel. So if Rogine mentions something that you have a question about, go ahead and type it in there before you forget. And I'm going to be collecting all the questions and we'll ask them to Rogine at the end of the webinar. Okay, this ends our introduction. So without further delay, let's get started. Rogine, it's over to you.
Thank you very much, Lauren, for the introduction. So as Lauren mentioned, today we will go over the test method ASTM D7823, which provides a procedure to identify and also quantify phthalates by thermal desorption gas chromatography mass spectrometry. 6 phthalates are used to demonstrate the use of this procedure, and the phthalates are BBP, DBP, DEHP, DNOP, DINP, and DIDP. And here you can see the actual official title of the method from the ASTM website that is also available for you to purchase. So as we all know, phthalates, which are phthalic acid esters, have been used to manufacture a wide range of consumer products. They can be added to plastics to make them more flexible and harder to break. And although the widespread use of phthalates in polymeric products has been largely discontinued, but they still pose a risk to human health. Phthalates are actually easily released into the environment because they're not covalently bonded to the polymer. So as the result, exposure can be through direct contact with food, water, and the atmosphere. Several phthalates are regulated on a global scale. United States, Canada, European Union, Japan, and many other nations have actually banned the use of and passed regulation designed to monitor the concentration of phthalates in consumer products. And here you can see some of the regulations with the references, substances, and requirements as example. So it is very critical for different manufacturers to comply with these regulations by having the capability of accurate measurements of these phthalates. One of the traditional techniques for analyzing phthalates is solvent-based techniques to extract the phthalates from the polymeric mixture. The extract is then analyzed using GC or HPLC to separate and quantitate the individual phthalates. These traditional techniques are most of the time time-consuming, costly, and they do not always completely isolate the phthalates from the polymeric mixture. As a result, reproducibility and accuracy can become challenging. On the other hand, thermal desorption uses sufficient amount of heat to thermally vaporize a sample without oxygen and thermally extract or isolate the additives. In our case, the phthalates from the polymers and heavier portions of the sample. So as we just mentioned, the traditional techniques require large amount of solvent, excessive analyst time, and can be prone to contamination and the other errors. The result of this additional sample handling can reduce laboratory productivity, and the information obtained could exhibit poor precision and accuracy in most cases. So that's really where thermal desorption GCMS comes in place as a green alternative to solvent-based extraction techniques. Thermal desorption GCMS is actually ideal for any type of solid samples. It requires very small to no amount of solvent. It adds efficiency to your laboratory and also improves data quality. This technique is used in other applications and industries, as you can see here. For example, brominated flame retardant and rubber manufacturers also can use this technique. But today we will mainly focus on phthalates in polymers, especially in a PVC type sample. So before we go over the application, we're just going to talk a little bit about thermal desorption GCMS. And here is the system configuration for a microfurnace pyrolyzer, which can perform pyrolysis and thermal desorption type analysis. The microfurnace pyrolyzer, which is shown as number 2 in this figure, is used as a programmable temperature inlet to your GCMS system. It is directly connected to your GC injection port, so there won't be any transfer line, there is no active site, and there is no cross-contamination. You can also see some of the other accessories in this figure. For example, the microjet cryo trap that uses liquid nitrogen to trap and focus lights and volatiles at the head of the GC column for you. The selective sampler that is used for the hard cutting mode of operation. The AutoShot sampler for automating the analysis of up to 48 samples. The vent-free GCMS adapter that allows switching the columns without venting DMS, and the F-Surge interpretation libraries to identify polymers and additives. So what sets a microfurnace technology apart from the other pyrolyzers in the market? With a microfurnace, sample introduction is nearly instantaneous. The sample is actually placed in an inert sample cup and is held near ambient temperature in helium. The microfurnace is then preheated to the desired temperature, which is precisely measured with a thermocouple sensor. The sample cup then dropped into the quartz pyrolysis tube where the sample is pyrolyzed. The pyrolysates are then swept directly onto the GC column for separation and detection by MS. This technology is based on a continuous mode pyrolysis, where all the pyrrolysate as they are generated directly and continuously transfer to the GC column. The sample is held at an ambient temperature while the furnace is preheated, so the sample is not going to be exposed to any heat prior to the analysis. And as a result, there won't be any degradation or any evaporation of the lighter compounds before the analysis starts. Also, with microfurnace technology, you can perform thermal and multiple separation analysis. For example, you can perform evolved gas analysis, thermal desorption, flash pyrolysis, double shot, and hard cutting. But today, we will focus on the evolved gas analysis and thermal desorption modes of operation in microfurnace. Now, to chemically characterize an unknown sample, we have developed a series of techniques that is called the method map. The method map provides two simple steps for determining the organic composition of any type of unknown sample, liquid, solid, or even gas type sample. Evolved gas analysis, which is known as EGA, is your first step, which provides a clear picture about the thermal profile of your sample. EGA is a thermal analysis very similar to TGA, a thermal gravimetric type analysis. But with EGA-MS, you can identify the chemical composition of the evolved gases at different temperature. The second step is then to use your EGA thermogram to define the thermal zones of interest and then perform separation analysis on your sample. So EGA really guides you on what to do next. It will show if a thermal desorption, hard cutting, or flash pyrolysis is needed, or if a combination of these techniques is required. Now that we have a good understanding of microfurnace pyrolyzer and its capability, let's go over the actual phthalate application. So the ASTM D7823 sample preparation specifically calls for the dissolution of the polymer in a suitable solvent such as THF. However, subsequent studies have also shown that meaningful data can also be obtained when the polymer is analyzed directly. So here, as shown here, there are two techniques for sample preparation, direct and thin film. Analysis of the solid is often referred to as a direct analysis, in which you can simply crush and powder your sample, and then you can place a few micrograms directly inside your cup. On the other hand, you can also use a thin film method, in which you dissolve the powdered sample into solvent and then analyze a microliter aliquot of a quantitative solution of the sample. The RST percentage of DEHP in 4 runs of thin film and direct approach was calculated to compare the influence of the sample preparation method on the precision. The thin film method is an aliquot of a solution, as we mentioned, that is by definition homogeneous, whereas the direct method is a random sampling of particles which could lack sample-to-sample reproducibility depending on the sample type. The RST percentage of DEHP for the thin film is about 1.1%, whereas the direct method generates a 4.7% RST. So to show the importance of sample homogeneity in measurement accuracy, DEHP was also quantified in each part of this plastic toy shown here. You can see that different ppm amounts were detected in each color part of the toy. So again, it is very important always to consider sample homogeneity when you're performing quantification analysis. And sample homogeneity can be accomplished using various methods, including cryomilling, grinding, averaging the results from the analysis of multiple samples, and in this example, dissolving the entire sample in a known volume of solvent. But regardless of how the sample is homogenized, only microgram quantities are analyzed using the thermal Desorption-GC. As we just learned from the method map concept, Evolved gas analysis, known as EGA, defines the optimal thermal desorption zone for thermally extracting the phthalates. EGA is a rapid screening method that utilizes the temperature programmability of the microfurnace pyrolyzer. Now, to perform EGA, a deactivated stainless steel tube connects the injection port to the MS. The sample is heated, typically from a low temperature to a higher temperature. And as the temperature increases, gases evolve continuously from the sample, pass through the tube, and are detected by the MS. A plot of sample temperature versus detector signal is then called an EGA thermogram. Now, to further analyze the sample, the EGA tube is switched to the GC separation column using the vent-free GCMS adapter. The microfurnace is then programmed to the desired or optimal thermal desorption temperature range, and a separation analysis is performed on the sample to thermally extract additives and lighter compounds from the heavier and polymeric portion of the sample. The EGA thermogram of a PVC sample heated from 100 to 700 C with a ramping rate of 20 degrees per minute is shown in this figure. Extracted ion chromatogram, or EIC, are also used to identify the thermal zone over which the phthalates evolved from the EGA thermogram. As we all know, ion 149, which is a common to all of the phthalates of interest, was used here to identify the phthalates envelope. Now, in this example, DOA, which is a common plasticizer used in manufacturing of flexible plastic toys, or medical devices, or food packaging, it actually desorbs along with the phthalates. So to identify and quantify the phthalates in the sample, it is necessary to either chromatographically separate the DOA isomers from the phthalates of interest, or you can use ions that are present in the phthalate mass spectra and not found in the DOA spectra. Also here, I want to mention one of the most important advantages of the thermal desorption over the traditional solvent-based technique is that with thermal desorption, only the portion of the desorbed sample is transported to the column. Now, if you look closely here at the thermal desorption zone for the phthalates, you'll notice that only the phthalates thermally evolved from the sample at about 320 degrees Celsius. And this means that the polymer remains in the sample cup and is not introduced into the GC inlet column, or MS. And because the bulk of the sample, which in this case the polymer fraction, remains in the cup, more sample amount can also be placed in the sample cup to improve the signal to noise of the target compounds. So this is the desorbed portion of the PVC sample shown on a previous slide. The identification of each compound is based on the retention time, the presence or absence of the quant ion, and one other confirming ion, as you can see here. And as we all know, polymers are loaded with additives. DINCH is commonly used, and it actually co-loads with several of these phthalates. So it is necessary to find unique ions to use for the quantification. Also, using a standard addition to calibrate helps to take matrix interferences into the account. A section in ASTM D7823 shows the analytical precision of thermal desorption GCMS when analyzing the regulated phthalates, and you can see that table here. This is a summary of run-to-run precision for 3 different PVC samples. Each PVC sample contains one additional plasticizer that actually co-desorbs with the phthalate. Phthalate concentration is 1000 ppm. And this data shows how a unique quant ion can be used to calculate the phthalate concentrations with high accuracy and low RSD percentage. This figure summarizes the data quality differences in accuracy and precision between the thermal desorption and solvent extraction techniques. So wet chemical methods or those solvent extraction techniques often result in low values for the concentration of the volatile phthalates. These can be attributed to losses during sample preparation. And as shown in the ASTM figure here, you can see when solvent extraction was used, phthalates such as DBP, BBP, and DHP, they had pretty high value. And actually, you can see that they are with high RSD and lower value than the theoretical value of 0.1%. Also, with solvent extraction approach, high concentration values for DNOP, DINP, and DIDP are resulted, which is due to the interference from the co-loading with DINCH. On the other hand, the thermal desorption technique that is shown here as a blue curve gives an almost constant response for all the 6 phthalates, very close to a theoretical value with an average precision of 1.8% RSD. And this accuracy can be obtained as the phthalates are thermally extracted from the mixture and unique quantification ions are used to distinguish them from one another. As we learned, individual phthalates are identified using both retention and mass spectral data. However, attention must be given to the possibility that they are similar compounds which co-load and have similar mass spectra to the phthalate of interest. One such compound is DOTP, which is very similar to DNOP. With thermal desorption GCMS, you can actually easily and accurately identify DNOP and DOTP, even though both compounds co-load with various DINCH isomers by using M/Z of 279, which is free of interference. In addition, DOTP has a 261 ion, DNOP and DINCH do not, which provides a confirming ion for DOTP. ASTM D7823 is written specifically for phthalates in PVC. However, the solubility of phthalates in most non-crystalline polymers could be the same. As a result, the thermal desorption temperature range is independent of the polymer substrate. When using thermal desorption to isolate beyond the scope of this ASTM D7823, or if they are incorporated into a polymeric base that has not been evaluated, it is recommended to verify the optimal thermal desorption zone using your EGA-MS first. In addition to the ASTM D7823, we also have IEC 62321, which is for identifying phthalates in power cord, so that's for electronic type devices. The IEC method uses the same concept as the ASTM by using EGA as the first step for identifying the optimal thermal zone to thermally extract the compounds of interest. Once the EGA thermogram is obtained, the additives, in this case the phthalates, were thermally isolated using separation mode of operation from the microfurnace. Well, at the end, in summary, ASTM D7823 is based on a thermal desorption GCMS technique. The method is suitable for an extended list of phthalates in a wide range of polymeric compounds. The entire analytical sequence is performed in a single step in which a known weight of a solid sample or a known volume of a quantitative solution is placed in a sample cup, which in turn is placed into the autosampler carousel. Thermal desorption also eliminates conventional sample preparation. The sample is heated so the phthalate is thermally dissolved from the polymer. It is fast, it uses a minimal volume of solvent, eliminates the need for expensive glassware, and more importantly, delivers accurate and more reproducible measurements. And with that, I'd like to use this opportunity to thank everyone for joining us today and give the mic back to Lauren.
Awesome. Thank you so much, Rogine. So before we dive into the Q&A, I wanted to, oh, perfect. There it is on the screen. I wanted to dive into an exciting training class that we have coming up at Quantum Analytics. If you or someone on your team is considering becoming a frontier pyrolysis super user, training is a major factor to consider. You want to be able to understand how to use the equipment and maintain it and follow best practices. We are offering a 3-day pyrolysis GCMS training course at our Woodlands, Texas facility from April 23rd to 25th. Registration is open. This is an awesome program. It always tends to sell out. So if this is something that you're considering, um, we do have spots available in this class. So go ahead and let us know if you want to get all registered. We can help you out there. But yeah, it includes both classroom and lab environment, and you're going to learn instrument fundamentals, operation procedures, maintenance best practices for the frontier pyrolysis system. So this is an awesome class. All right, it is time for some Q&A. So if you have any questions for Rogine, type those questions into the question box you see in the GoToWebinar interface, and we will add them to the list here. All right, so first up, Rogine, what is the difference between heart cutting mode of operation and double shot analysis?
Okay, so with the double shot analysis, as the name mentioned, you can perform about 2 analyses on the same sample. Typically, you do thermal desorption followed by a flash pyrolysis. So all the mode that we discussed today in terms of thermal desorption, you would be using a double shot mode where you can actually do thermal desorption, which is thermally extract your additives, and then perform even flash pyrolysis on the same sample. So you obtain 2 separate chromatograms. One is your thermal desorption chromatogram, and then one is for your polymeric heavier fragmentation of your sample. That is called the flash pyrolysis, the pyrogram for your polymers. But with the hard cut, now imagine if you want to perform up to 8, for example, so you could do multiple analysis on the same sample in a way that you have initial temperature to the end temperature. So it's like a temperature programming up to 8 analysis. That's where it's called hard cutting or the thermal slicing. When you obtain your EGA thermogram, depending on your EGA thermogram, you can now thermally slice your EGA thermogram and perform separation analysis on each zone from your EGA thermogram, and that is called the hard cutting. Typically, hard cutting is for reverse engineering, deformulation type analysis, very detailed information about the chemical composition of the sample, additives, polymers, mixture, anything that you have. Whereas a double shot is mainly focusing on thermally extracting the additive and volatiles from your polymeric portion. So you will be performing 2 analyses on the same sample.
Fantastic. Next question I have here is, were you able to determine the TD efficiency for different materials?
So yes, there are other applications that show that. Today we focus on that ASTM for that specific PVC, but these TD thermal desorption, you could perform quantification work, and yes, there are other applications that we have. So if you connect with us afterward, we can also share some of those other application examples with you.
Great. And how do you determine whether the TD can desorb all the target compounds from the material?
So it really depends on what type of material or compound that you're trying to go after and identify. And once you perform that EGA, which is a thermal analysis, it gives you a good understanding about the thermal profile or the thermal behavior of your sample. Even if they are, for example, 2 compounds that they're co-loading from your EGA, once you obtain that thermogram, you'll be able to identify the M over Z or kind of get an understanding of how that thermogram looks like in terms of the chromatography, in terms of the MS spectra of it. And then once you have that, you have to obtain the optimal temperature zone to be able to thermally extract those specific additives. For example, we have a good example in eyeliner. So we did a analysis of an eyeliner for a cosmetic consumer product where there were mix of additives and mix of polymer. with the EGA-MS, we were able to actually see about 5 or 6 hump or peak or zone, however you want to call it, from your EGA-MS. And then we were able to obtain the separate thermal desorption or the separate temperature zone for each of those hump or zone from your EGA-MS. Then you basically zoom in, either do a TD or do a hard cut to be able to now do a separation on those specific temperature zone that you can thermally extract your additives. Also, we have customers, for example, if you're in coating and some of the material, the additives, depending on how hard that is, because sometimes it might be on the surface or depending on the metrics of the sample might be harder to extract them. Typically, holding time will help a lot by holding at a specific time for a few minutes, then performing thermal desorption to make sure you can get as much as possible of those additives out from your sample.
And then the question here, this might be a follow-on to that, is how do you know 100% of the target compounds are extracted by TD?
Well, I mean, in this point, you're just trying to kind of quantify and analyze whatever that you're trying to thermally extract. So based on your EGA, you have that temperature. And when it comes to, you know, how do you know it's coming out? It goes back to the basic of you know, every compound, when you're doing GCMS on it, depending on a boiling point of it, depending on a retention time, if that's a specific boiling time, if that's the optimal temperature zone that you have, you can thermally extract it. However, there are cases where, for example, if you're dealing with some of those bigger, higher boiling point additive, for example, it's possible that some of it will come in one zone of your hard cut, and then the other portion of it or the other fragmentation come in the second portion or the second thermal zone, if that makes sense, of your hard cut. So the main key here is to identify the temperature that you'll be making sure it's not too low or too high, to make sure that you can thermally extract and isolate that specific compound or additive group from your polymeric portion of the sample.
Awesome. And you mentioned the RSD. How about the accuracy of phthalate analysis?
So here today, we only show basically just a few figures of the related to the RSD, but on actual ASTM methods, it talks about that. It gives a lot more information. So of course, it goes more into in-depth detail about sample preparation, calibration curve, accuracy, and precision. So we show a couple of examples here for those 3 PVC samples that were also added with some type of a plasticizer. But again, here today, we only show the RSD percentage. For more detail, you can go and take a look at the ASTM method.
Awesome. What is the typical sample amount? Can I place more samples if I am only performing thermal desorption?
Yes. So if you decide to not do a bulk pyrolysis, as we mentioned, which means if you decide to not analyze your sample at a pretty high temperature. When I say bulk pyrolysis, is about 550, 600 C. So if you try to stay below them, typically from 100 to about 400 C is the thermal desorption mode, you could put more sample inside your sampling cup. But for the most part, we don't recommend to put somewhere between 100 to 200 micrograms, especially at the beginning. So you don't want to overload your system, especially your MS. But depending on the type of analysis, yes, you can perform more sample. You can place more sample inside the cup.
Awesome. And then can I also analyze light additives using thermal desorption GCMS?
Yes, depending on how light you are thinking to analyze the additive, as we show from the system configuration, there is an accessory or an add-on that is called the microjet cryotrap that uses the liquid nitrogen, and it will trap and focus those volatiles and light compounds for you at the head of the GC column. So because it is using a liquid nitrogen, it goes down to -196 degrees Celsius. So you'll be able to trap and focus those type of light and volatile compounds.
Great. And if I have an unknown sample and want to identify the polymer, should I start with the flash pyrolysis mode of operation?
You could, however, if it's completely unknown, you have to guess the optimal temperature for your pyrolysis. And that goes to the challenge of if you don't know what's the optimal temperature for your pyrolysis is, if you just do it by guessing, you could do over pyrolysis, which means you heating your sample more than you should. You're breaking down your polymer into a lot smaller fragmentation that is harder for you to identify those pyrolysis to the corresponding polymer, or you'll be performing under pyrolysis, which is you're not applying sufficient amount of heat to your sample to break down the polymer into adequate type pyrolysis or fragmentation. So even if you are trying to do a polymer identification, typically, yes, flash pyrolysis is the first technique to go, but we highly suggest you would use your EGA first. So run EGA on your sample, better understand the thermal profile of your sample, then identify what's the optimal temperature for your flash pyrolysis, and then perform a flash pyrolysis on your sample. And also in some cases, we also have some customers where they only do a polymer analysis. However, they would use the double shot still. Because with the double shot, what you're doing is, especially if your sample is a mix of additives and polymers, you would thermally extract the additive first, and then you perform flash pyrolysis on the heavier polymeric portion. So per se, your pyrogram, it's a cleaner pyrogram. It corresponds to the breakdown and polymeric portion of your sample rather than only doing flash pyrolysis and obtaining one pyrogram that has all the additives and breakdown of your polymer in that one pyrogram.
Awesome. And then what MS library, search library can be used for identifying additives and polymers in general?
In this example shown here today, we were using fsearch interpretation libraries, fsearch 3.7, that has a search engine with 4 unique libraries of EGA MS, additive MS, polymer, and pyrrolysate MS library. You can also use NIST, of course, but with fsearch, the reason it is specifically designed for polymers and additive is that not only with fsearch you can identify this peak, for example, correspond to this specific compound, but also fsearch tell you where that source of origin of that pyrrolysate is, where that pyrrolysate is coming from, which polymer is coming from. Because again, with pyrolysis, you are breaking down your polymer into smaller fragmentation that are called pyrrolysate. And then you use those pyrrolysate to identify the corresponding polymer. So fsearch really helps you by telling you this peak corresponds to this specific pyrrolysate or compound, and this could be coming from this specific polymer. So fsearch typically is used for polymers and additive analysis.
Fantastic. Well, I think that is it. Before we close, I wanted to thank everyone for attending today's session. And thank you to you, Rogine, for sharing your knowledge and expertise with us. This was an awesome session. We encourage everyone to visit our resources page on lqa.com for future webinar details and to access our library of recorded on demand sessions. Thank you again, and everyone have a great rest of your day. Thanks, everybody.